Hello friends, welcome back to the video series on design of steel structural elements. In the previous videos we have seen how to find out the design tensile strength of a plate and that of an angle. Right, now the angle and the plate sizes were given to you and you were supposed to find out the design tensile strength and also the type of connection, that is the bolted, how many number of bolts are there, what is the pattern of the bolt. Everything was given to you and you were supposed to find out the design tensile strength of that plate or that of an angle. Now in this video what we will do is we will actually design a angle for a given load. It's a reverse type of problem as compared to the previous problems. It's a reverse thing. The load is given to you and you have to find out the particular suitable angle for that. Now here this problem is design a suitable design a single angle, right? We need to design a single angle section for a tension member of a roof truss to carry a factored load of 225 kN and the load is given as 225 kN. The member is subjected to the possible reversal of stresses due to wind action. The effective length of the member is 3 meters, right? And you need to use bolts of M20. Sorry for that, I need to just type here M20. Okay, right? So and the bolt grade is you have to use is 4.6 and you have to design a particular section. So we'll see how to do that. So now to start with, in case of a design problems in tension members, I have to take the criteria of yielding of cross section. Okay, I have to take the criteria for yielding of cross section. So yielding of cross section says that means the design tensile capacity of a member as per yielding of cross section says that TDG is equal to AG Fy, okay, divided by gamma m naught. AG Fy divided by gamma m naught, right? Now okay, now here what we'll do is here we'll assume that the given load, which is 225 kilonewton, is nothing but the full strength of that angle, right? Full strength of that angle, that is 225 into 10 is to 3 in newtons. AG I don't know because I don't know what is the size of angle I have to use, so I will keep it as AG itself. I will put this as 250, that is 250 megapascals divided by gamma m naught is 1.1. Now with this relation I can easily find out what is the AG required for that. So if I do that, it comes out to be something around 990 millimeter square. So 990 millimeter square. Now what I will do here is I will just increase this AG by something around 25%, right? Increase the AG by 25%. I will tell you why should I increase that. The reason for increase is if I try to find out an suitable angle which is having a cross section of 990 directly from the steel table, if I do further calculations, it happens so that I may be supposed to give some bolts. Yeah, of course I should provide some bolts. So when I provide some bolts, what happens? The gross area once again reduces. So it reduces lesser than the required one. So at that time the angles may fail. There are chances of failure. So instead of redoing the calculation, what I will do, initially itself I will be a little bit on a conservative side and I will just go for some higher size, that is 1.25 times AG. So if I increase that AG by 25%, I get AG required as 1237.5. millimeter square. Now what I should do is I should actually check the steel table for an angle, single angle, which gives this much of area. Now what I will do is I will try to use an unequal angle, unequal single angle. I'll try to use an unequal single angle. So I should open the steel table. Okay, instead of that I can go for SP6. So I have opened the section which contains rolled steel unequal angles, and I will try to find out that much of area. So how much I should get? It should be 1237.5 millimeter square. If I divide it by 100, that is in terms of centimeter square, because in SP6 they have given the values in terms of centimeter square. You can see that cross section area in centimeter square. So I should search for an angle which gives area just more than 12.37. So I will just come down, look for that kind of an angle. So here I didn't find, so I should go for the next page. Okay, so let me check here. Give me a moment. So let me check that. Okay, right. Now here I am able to find an angle called 100 by 65 by 6, 100 by 65 by 8, which is having a cross section area of 12.57. It may pass, so let us try with that. So let us try 100 by 65 by 8. Try ISA 100 by 65 by 8. So if I do that, so actual AG provided will be, I will check, 12.57, means it is 1257 millimeter square in terms of millimeter square. 12.57 is in centimeter square, so 1257 is in millimeter square. Right, so now I have arrived at that angle, that is ISA 100 by 65 by 6. Okay, now I will try to find out how many number of bolts are required to connect this angle to a gusset plate to take a load of 225 kN, right? So how many number of bolts are required? So I will just find out that. Number of bolts required to connect ISA 100 by 65 by 8 to carry a load of 225 kilonewton, to carry a load of 225 kilonewton. So what I will do, I will assume something around, I will try to use M20 bolts. Okay, here he has given what kind of bolts you should use. Yeah, he has told that you should use a M20 bolts of grade 4.6. If it is not given, so you can go with your choice. So I will use M20 bolts of grade 4.6. So actually I directly know what is the bolt strength for that. You should actually calculate this one. So since I know it, I can find it 46.4 kilonewton in single shear, because if I connect this bolt to that angle to the gusset plate, it will be in single shear, because you can see here. So if this is a gusset plate, if this is a gusset plate, and if this is an angle, right, so the bolt will be provided here, so there will be only one single shear plane, so it is a single shear problem. Okay, so number of bolts will be number of bolts required are, so the total load is 225 divided by 46.4, so I'm getting out to be 4.84. So therefore provide 5 numbers of bolts in one row as shown in figure. Okay, right? So I need to provide 5 numbers of bolts in one row as shown in figure. So I will try to draw that figure on connection and how I am actually connecting that. So this first I am trying to draw the gusset plate. This is the gusset plate. To which I am actually connecting the angle. Okay, so should show double line, that is the thickness of the angle. Discontinuity, I will show 4 numbers of bolts. This is a line of action of force. I should show those bolts here. Okay, 1, 2, 3, 4 and 5. 5 numbers of bolts. Okay, so this is the gusset plate. Let me assume that it is something around 10 mm thick. Okay, so this is an angle ISA 100 by 65 by 8. Now actually how should I connect that for an unequal angle? I also already told that in the previous videos that whenever it is an unequal angle, try to attach the longer leg to the gusset plate and let the shorter leg be an outstanding leg. So I am here, I am attaching a 100 mm leg to the gusset plate and I am keeping 65 mm leg as the outstanding leg. Now this is actually the connection. So this could be 225 kilonewton. Now this is actually the connection. So an angle which can carry a 225 kilonewton with 5 numbers of bolts, but I have to prove that this angle, that is ISA 100 by 65 by 6 with 100 mm leg connected to the gusset plate of 10 mm thick with 5 bolts in the end connection, can carry a load of 225 kilonewton, right? And I also need to mention the edge and pitch distances. So they are actually standard edge should be 1.5 times d and pitch should be 2.5 times d. So let the edge be 30 and let the pitch be 50. So 4 pitches are there of 50 mm each, right? Okay, now I will try to find out I will try to prove that this angle with this connection is safe. So how should I do that? Now we should once again go back to our previous types of calculation. That first I need to find TDG. Okay, TDG is equal to AG. AG is actually the gross cross-sectional area of the angle. So gross cross-sectional area of the angle we know, which is 1257. 1257 multiplied by yield strength, that is Fy, divided by gamma m naught, which is 1.1. So this will obviously pass, but still we need to do that calculation and show it. So it is 285.68. So it is 285.68 kilonewton, which is more than 225 kilonewton. Hence the angle is okay as per yielding of cross section, but still we need to check as per net section of rupture. So TDN. So the formula for TDN is, I'll just write out the formula for TDN. Okay, right, 0.9 FUANC, 0.9 FUANC divided by gamma M1 plus beta into AGOFY divided by gamma M0. Okay, so I'll quickly go through all these things. So ANC is net area of the connected leg. So since the 100 mm leg is connected to the cassette plate, so I should use here 100 minus, so one bolt is coming in the line which is of 20 mm, so bolt dia will be 22. Okay, 100 minus 22 minus half the thickness of the angle, which is 8/2, this multiplied by the thickness of the angle, which is 8. So this comes out to be 592 millimeter square. Similarly, I will calculate AGO, that is gross area of the outstanding leg. Outstanding leg width is 65 minus half the thickness of the angle, no deduction of any holes, multiplied by 8. So 65 minus 8/2 into 8, so I am getting 488 millimeter square. Okay, so beta I will calculate 1.4 minus 0.076 W by T BS by LC Fy by Fu. So beta is equal to 1.4 0.076. So W is the width of outstanding leg, which is 65, divided by thickness of the angle is 8. Okay, then BS, so I should calculate the value of BS. So BS is W plus Wi minus T. So this is actually Wi. So Wi is, this side it is 45, so this side it will be 55. You can see from the steel table, you can get these values. So it is W is 65 plus 45 minus 8, so I am getting 102. Okay, so it is 102 divided by LC is the distance between the outermost bolts, which is 4 into 50, which is 200. So Fy is 250 divided by 410. So if you calculate that, beta comes out to be, I will just calculate that, 65 divided by 8 multiplied by 102 divided by 200 multiplied by 250 divided by 410. Okay, so this multiplied by 0.076, so the whole answer is to be deducted from 1.4, so I am getting 1.2, beta as 1.2, right? Okay, so we'll plug all those values in that equation for TDN, and let me find out the value of TDN. I need to plug the value for ANC, AGO and beta in that equation. So it is 0.9 into 410 into ANC is 592, so divided by 1.25 plus beta is 1.2. 1.2 multiplied by AGO is 488 multiplied by 250 divided by 1.1. So I'm getting out to be 307.85 kilonewton, which is once again more than 225 kilonewton. So it is okay from the rupture at critical section point of view. Still, I need to also cross check for the block shear. Check for block shear. So I will write the formula for block shear, that is TDB1 is equal to, okay, so formula for TDB1, AVG Fy divided by root 3 gamma m naught. AVG, here it is, AVG Fy divided by root 3 gamma m naught plus 0.9 ATN FU .9 FU divided by gamma m1, right? I will also write for the formula for TDB2. TDB2 is 0.9 AVN FU divided by root 3 gamma m1 plus ATG Fy divided by gamma m naught. Okay, so I will calculate the value for AVG and all other things, but before that I will just take this figure below. Okay, so I will mark the block shear. So the shear plane will be always parallel to the applied load accompanied by a tensile plane. So this will be the block of that material which will come out. So this we have already seen in the previous videos. So I will just calculate the values for AVG. AVG is equal to, so it is the shear plane length is from here to here, it is 230. So 230 into 8, that is the thickness of the angle, coming out to be 1840 millimeter square AVN. Okay, so 230 is the shear plane length minus, I have to deduct 4.5 bolt dias, this multiplied by the thickness. So this comes out to be 230 minus 4.5 into 18 multiplied by 8, so 1192 millimeter square. Similarly, I will calculate ATG, so which is 55 into 8, which is coming out to be 440. Similarly, ATN is 55 minus 0.5 dia I have to deduct. This is the length of the net tensile plane multiplied by the thickness of the angle. 0.5 into 18 multiplied by the thickness, which is 368 I am getting. So you should just plug all those values in that equation for TDB1 and TDB2. So let me check how much I will get. I'll put this down. Okay, so I will calculate values for TDB1 and TDB2. So AVG is 1840 multiplied by 250 divided by root 3 into gamma m naught 1.1 plus, okay, 0.9. ATN is 368, okay, multiplied by FU is 410. This divided by gamma m1 is 1.25. So I'm getting this to be 350 kilonewton, which is greater than 225 kilonewton. So it is okay. So let me check for TDB2. 0.9. AVN is 1192 multiplied by 410 divided by root 3 into gamma m1 is 1.25 plus ATG is 440 multiplied by 250 divided by gamma m naught is 1.1. So this is 303.15. which is once again greater than 225 kilonewton. So it is okay. So we can see that so all TDG, TDN, TDB1 and TDB2 are all more than 225 kilonewton. Hence this angle ISA 65 by 65 by 8, ISA 100 by 65 by 8 with 100 mm leg connected to the gusset plate of 10 mm thick with 5 bolts in one row can take a load of 225 kilonewton. So the design is okay. So this is how we need to design. So in the first initial stages you have to arrive at a section based on this formula, that is TDG. You have to find the AG required, increase it by 1.25 times, that is 25%, and you will get one figure. So choose an appropriate section. Okay, then you should actually find the number of bolts required. So here it is, provide the number of bolts required. Then you have to arrange those bolts according to your wish. Then you have to prove that this angle with these many number of bolts is able to carry the applied load. So that is, you have to check for TDG, find TDG. Okay, then you have to find TDN, which is coming out to be this much. Then you have to find TDB1 and TDB2, and all these values should be more than 225 kilonewton, that is the applied load. Then only you can say that your design is okay, right? So this is how we approach design of tension members problem. So hope you understood. So we'll solve one more example on this type in the next video. Till then, thank you, bye.